Have you ever just stopped and wondered how the internet works? I mean, how your data finds its way through this massive global maze in like the blink of an eye? Well, today we're going to pull back the curtain on one of the key rule books that turns all that potential chaos into a smart, self-organizing neighborhood. Okay, let's get into it.
Here's our game plan. First, we'll look at why we even need rules by exploring the chaos of an unchecked network. Then we'll introduce the hero of our story, OSPF. We'll see how routers make friends, pick a leader, and then map out the best routes. And finally, we'll wrap up with why this whole system is so incredibly important.
All right, first things first. Before we can really appreciate the solution, we have to understand the problem. And believe me, without rules, a network is pure, unfiltered chaos.
Seriously, think about it. You hit send on an email, you load a video. How does that little packet of data know the single most efficient path to take, potentially cross continents, when there are millions of possible routes? It's not magic, but without a system, it would be an impossible task.
Picture a major city, but with no traffic lights, no stop signs, nothing, just a total free-for-all. It'd be instant gridlock, right? Well, that's exactly what happens in a network. If every single device is just shouting information at every other device all at once, you get what's called a broadcast storm, and everything just grinds to a halt.
So how do we fix this mess? How do we bring some sanity to the chaos? Well, we need a rulebook. And one of the most powerful and popular rulebooks out there is called OSPF.
OSPF stands for Open Shortest Path First. Now, it's a specific type of protocol called a link state protocol. Here's what that means. Instead of just knowing the very next turn to make, every router using OSPF has a complete live map of the entire network. It knows about every road, every intersection, and all the traffic conditions in real time.
The name itself actually tells you a ton. Open is a big deal. It means it isn't some proprietary tech locked down by one company. It's an open standard anyone can use. And shortest path first, well, that's its superpower. It uses a brilliant algorithm that works just like the GPS in your car, constantly calculating the absolute best route from A to B.
So let's get into a few key details. As we said, it's a link state protocol, so it has that full map view. Now, it measures how good a path is using something called cost, and we'll dig into that in just a second. It also speaks its own language, sending out little hello messages to find other routers. And finally, in the world of networking, it has a very high trustworthiness score, an administrative distance of 110. That's really, really good.
Okay, so the very first step in building this smart neighborhood is for the routers to introduce themselves. They have to get acquainted and become neighbors.
But, they're pretty picky about who they become friends with. It's like they have a secret handshake. As this checklist shows, a bunch of things must match. They have to be in the same network segment, the same area, and agree on timers and passwords. But one thing must be unique. Every router needs its own ID. Only when all these rules are met can they start building trust.
And this process of becoming neighbors isn't instant. It happens in stages, almost like a real conversation. It starts at down, where a router is all alone. Then in it, hey, I hear you. Then two-way, awesome, we can hear each other. From there, they figure out who shares their map first, exchange the highlights, and then all the details, until they hit the full state. That's the goal, 2 routers with identical, perfect maps of the network.
All right, so our routers are neighbors now. They're all on the same page. The next step is to get organized. To stop that chaotic broadcast storm we talked about, they need to elect a leader.
Think of it like this. On a network segment where lots of routers are connected, it would be like a party where everyone is yelling at once. It's just noise. So instead, the routers hold an election to choose a spokesperson, the designated router, or DR, and a backup, just in case. Now, everybody just talks to the DR.
So the DR's job is crucial. It becomes the one central hub for all routing updates on that part of the network. Instead of 10 routers all trying to talk to each other, they all just report to the DR, and the DR efficiently passes the information along to everyone else. It's a game changer for reducing unnecessary traffic.
So, how's this leader chosen? It's a democratic election. And as this chart shows, the rule is simple. The router with the highest OSPF priority wins. You can see here, routers A and B have the default priority of 1, but someone configured router C with a priority of 10. No contest. Router C is our new DR.
But you're probably wondering, what if there's a tie? That's a great question. You can't have 2 leaders, so there has to be a tiebreaker, right?
And there is. The tiebreaker is that unique router ID we talked about earlier.
If multiple routers share the highest priority, the one with the highest numbered ID wins the election. It's a simple, foolproof way to guarantee we always get one and only one DR.
Okay, we've come a long way. Our routers are neighbors, and they've elected a leader. Now for the main event. How do they actually use their maps to find the fastest path? Well, that GPS we mentioned, it doesn't measure distance in miles or kilometers. OSPF uses a special metric it calls cost. A great way to think about it is like the travel time on a road trip or maybe the tolls on a highway. The goal is always to find the path with the lowest total cost.
So where does this cost number come from? It's all about bandwidth, basically the speed of the connection, and lower is better. Check out this table. A super fast gigabit, or fast Ethernet link, has a low cost of 1. But a much slower, older Ethernet link, that has a cost of 10. This is why OSPF is so smart. It will naturally choose the faster link because it's the cheaper route to take. So let's tie this all together. We've built this neighborhood of routers that are friendly, organized, and have a shared map of all the best routes. What's the big payoff? Why does all this matter so much?
Because when you put all these pieces together, you get something incredible. An intelligent, self-healing network. If a connection goes down, if one of the roads on our map suddenly closes, the routers tell each other immediately. The algorithm recalculates and new best path is found. The network automatically finds a detour, often in just milliseconds.
And this gets to a really important concept from our source material: fast convergence. OSPF uses what are called triggered updates. That means the second a change happens, an update is sent out. There's no waiting. This ability to react and adapt almost instantly is what makes these networks so unbelievably stable and reliable.
So the next time you click on a website or stream a show, just take a second to think about this invisible neighborhood working for you. It's this incredible system of trust and communication that acts like the internet's own GPS, rerouting data around problems in the blink of an eye. And it really makes you wonder, what does it take to manage that kind of coordination, not just in a small neighborhood, but across the entire planet?